hope you enjoyed the first chapter. Now we're getting into the second chapter, Chemistry of Life. Okay, so we mentioned the matter and elements a little bit last time, and if you remember, matter is everything, pretty much everything that occupies space and has mass. So we have a solid matter, liquid matter, and even gas matter. So you can see carbon dioxide coming out of soda. Now, when we look at the building block for matter, the most fundamental unit is elements. So elements have specific chemical physical properties that cannot be broken down when you look at a chemical reaction. So I know it's a very kind of abstract description, but we'll have some examples later. The best example for elements is really this periodic table, right? When you look at this periodic table, we have how many elements? This is the last one, 118 elements. Now, not all of them are natural elements. They're not naturally occurring. Actually, we synthesize them in the lab. So only about 94 of these elements come from the nature. All right. So when you look at human body, these are the 4 most abundant elements. I don't know if you are familiar with any of these, but I'm sure most of us know oxygen, carbon, hydrogen. Now, nitrogen you might not be familiar with, but we actually have a lot of nitrogen, very abundant amount of nitrogen in the atmosphere. So when you breathe, most of the gas you breathe in is actually the nitrogen gas. Now, the first 3 are not surprising because our body consists of primarily organic molecules, and well, not primarily because we have a pretty high water content in our body, but when you look at the solids, the majority is organic biomolecules. So if you have to think about them, we have carbohydrates, we have proteins, we have nucleic acids, so those are the genetic materials, right? DNA, RNA. We also have lipids, fats, oils, those are lipids. So all those biomolecules, they consist of 3 main elements: oxygen, carbon, and hydrogen. That's why they're so abundant in our body. This is just some kind of interesting examples. There are some other elements that are also important. They might not come in the same quantity as those more common abundant elements, but they're also important for our normal body functions. So we have iron, right? When you eat a steak, there is a lot of iron in beef and red meat. Iodine, if you go to a grocery store to buy salt, you will see we have all kinds of salts, right? But some salts may not have iodine, some do. Now, I come from China, so when I was a little kid, sorry, I'm still trying to get over the cold. We had in the population, we had a deficiency in iodine. And now iodine is very important in synthesizing thyroid hormone. And thyroid hormone regulates your metabolism, which is a very important hormone. So because of the deficiency in iodine, a lot of Chinese people had dysfunctional thyroid. So a lot of them would have enlarged thyroid gland, right, to make up for the deficiency in iodine and deficiency in active form of thyroid hormone. So a lot of the salts will have iodine added. So this is a very cheap, easy way to get iodine in your diet. Okay. Now, fluoride, so comes from the element fluorine. We do put the salt form fluoride in toothpaste because it protects our teeth. Okay. All right, so those are some interesting elements. Now, just a quick overview on some of the definitions. Compound, you probably hear this a lot. People say chemical compound. So what does it mean? Now, when you have 2 or more elements in one chemical, then we call it a compound, right? So for example, water consists of 2 elements, right? Hydrogen and oxygen, so it's a compound. Benzene, carbon and hydrogen, again 2 elements, so it's a compound. Now for sulfuric acid, there are 3 elements, so again it's a compound. Now how about oxygen gas? Is it a compound? No, it's not a compound, and that's because there's only one element. Okay, so that's what compound means. Now, when we look at compounds, we can further divide them to organic compounds and inorganic compounds. So organic compounds are very important when we talk about life, when we talk about all the important functions. So organic compounds contain carbon atoms joined together by covalent bonds. So examples are gasoline. So I have a picture right here. So this is diesel gas. And you can see that it's really just a hydrocarbon, right? So you have carbon atoms bound together by covalent bond. See this, the line, the black line indicates the chemical bond. So you can see there are carbon-carbon bonds, right? Covalent bonds. So carbon-carbon bond, carbon-carbon bond. So if you have that characteristic, usually you can decide, okay, this is an organic compound. Now there is only one exception, and this is methane. Okay, so you can see that there is only one carbon in this compound, right? So there can't be a carbon-carbon bond. You don't have another carbon, but this is considered organic compound. Okay, so this is an exception. All the other organic compounds will have at least one carbon-carbon bond. We can add other elements to the organic compound to the carbon backbone, and this is still considered organic compound. So it doesn't have to have just carbon and hydrogen. It can have other elements as additions. Examples are oxygen, nitrogen, sulfur, chlorine, fluorine. So those are the common ones. Inorganic compound. So all compounds that are not organic compounds, then they're inorganic compounds. So example, sodium chloride, that's our table salt. Do you see carbon-carbon bond? No, so it's an inorganic compound. What about baking soda? Sodium bicarbonate? So think about that. Now you can say, hey, there's a carbon in sodium bicarbonate. How come it is not organic compound? Now again, the key is to look for at least one carbon-carbon bond, right? So you need carbon, it could be single bond, double bond, or even triple bond. So there's only one carbon there. Okay? So there's no carbon-carbon covalent bond, so it's not organic compound. Alright, now let's move on to atoms. So atoms are pretty important. They're the smallest unit for matter, the smallest building blocks. If you look at more closely, there are smaller particles in atoms, but atoms are the unit that can retain all the chemical properties of an element. Okay? So we're just going to call it the most basic, smallest unit of matter. So when you look at this picture, you can see three components in an atom. So the core, look at here, the core, this is called the nucleus. Now there are two components in the nucleus, the protons and the neutrons. Okay, so in the nucleus you have protons and neutrons. And then surrounding the nucleus you see this white cloud. Now they're just kind of trying to give you some color to kind of help you differentiate. But this cloud is forming by high-speed moving electrons. Okay, so basically you have the nucleus in the center, and then you have electrons moving very, very fast around the nucleus. Okay, so that's the three components. Electrons, they carry negative charge. Okay? And because they're so small, we just ignore their weight. So we're just going to say their mass is 0. And protons and neutrons, they do have mass. They each have 1. Now this is very arbitrary, so you just have to remember it. So 1 proton will weigh 1 unit, okay? And 1 neutron is the same weight, also 1. Now protons carry positive charge, exactly the opposite as the electrons. And the neutrons, based on name, they don't carry any charges, right? They stay neutral. So I'll tell you that each atom is electrically neutral. So that means the negative charges carried by the electrons have to be the same, equal, right, as the positive charges carried by the protons. So usually when you look at a neutral atom, the number for electrons and the number for protons should be the same. Okay, so this way the atom stays neutral. Okay, let's move on to the next slide. So this is carbon element. Okay, this is what you will see in the periodic table. Over here, this is 6, indicates the atomic number. So the atomic number is the same as the number of protons because you arrange the elements based on how many protons they have, right? So you go from 1 and then you go all the way to 118. The next one is atomic weight. So this equals the sum of the number of protons and sum of neutrons because only those two particles carry weight, right? The electrons are so small, we just ignore their weight. So for carbon, we have 6 protons, 6 neutrons. So together, the atomic weight will be 12. Okay? And you can say, oh, wait. Now here, this is not 12. This is 12.0107. So why is it not 12? And that's because we have isotopes. So it's the same element, but they weigh a little bit differently. So we have to take into consideration of the neutrons, the isotopes that have a different weight. Like some of the carbon isotopes may weigh 13 or 14. So that will kind of mess up the weight a little bit. So usually it's not exactly the sum of protons and neutrons. Okay, so for carbon, this is the information we have. I mentioned that the number of protons are equal to the number of electrons, okay, to make the atom overall neutral. So based on this information, you can actually calculate the atomic weight or number of electrons or protons based on the information available. Okay, so let's do a quick practice. Now for nitrogen, I'm going to tell you that the atomic number is 7. So the atomic number is the same as the number of protons, right? So this should be 7. So nitrogen has 7 protons. Okay. Now this piece of information is given, so there are 7 neutrons. What about electrons? Okay, so electrons, same as protons, so this also should be 7. Oh, this is a picture, so I can't really add a number to it. Hold on, let me do this. There you go. 7, so this should be 7. And what about electrons? We said it should also be 7, same as protons. And what about the atomic weight? So you're gonna come here. Atomic weight, number of protons plus number of neutrons. So 7 plus 7, and that should be 14. There you go. So that's the answer. Now, what about phosphorus? Protons, 15. So that means the atomic weight, the atomic number is 15 over here. So this should be 15. Neutrons, 15. So what's the atomic weight? 15 plus 15, that's 30. And the electrons should be the same as protons, so this is also 15. Alright, so we'll have probably 1 or 2 questions on the test on how to calculate the number of particles and the atomic weight. Alright, so here's the isotope. For each element, a lot of times you will see different forms of the same element. So when I say different forms, I meant more like different atoms. So all these different atoms will have 6 protons, so that means they are carbon element, but they have a different number of neutrons. So you can see carbon 12 has 6 neutrons, so 6 plus 6, the atomic weight is 12. We also have other forms, carbon 13, that has 7 neutrons, so the weight is 13, right? 6 plus 7. Over here, 6 plus 7. And then carbon 14 has 8 neutrons, so 6 plus 8, that's 14. So carbon 14 will be the highest or the heaviest form of carbon element. And in nature, carbon-12 is the most common one and accounts for almost 99%, right? And then 13 and 14 are pretty rare, but when you calculate the atomic weight for this element, you have to consider all the different forms, right?